In this video, we're going to look at standard heats of formation and then use those values to calculate our overall enthalpy change for our reaction. So first part is just to define what the standard heat of formation is. So standard heats of formation, it is an enthalpy change. So delta H, again, anytime you hear heat of, right, remember enthalpy is the heat of my reaction. So delta H for my enthalpy change. And then standard, so I'm going to put that not symbol there because I am at standard state. And then a subscript F for formation. And what the standard heats of formation is it's the enthalpy change for the formation of 1 mole of a substance in its standard state from the most stable form of its constituent elements in their standard states. And I'll write that in here in a minute, or in a moment. Often though it's hypothetical, like if I wanted to make sodium chloride, I'm not generally going to take sodium metal, that would be its standard state, and then chlorine gas, that would be chlorine standard state, and then combine them to make sodium chloride. It's how I would do it to get this value. That would be my definition of standard heats of formation, but it's not really practically, like in a practical sense, it's not how I would actually make sodium chloride. So often it's a hypothetical value, but we can use these values to determine our overall enthalpy change for our reaction. So the enthalpy change is kind of a mouthful. For the formation of 1 mole of a substance in its standard state from its constituent elements, so the elements that make it up, in their standard states. So again, an example, if I wanted to make sodium chloride, right, the one we just said, if I was to take sodium, which is solid, that would be its standard state, combine it with chlorine, which is a gas, that would be its standard state, and then make sodium chloride from that. And this isn't balanced, but it's just my example anyway. The amount of energy that we would need to do that would be my standard heat of formation, right? Because I'm making this from those guys in their standard states. Often it is a hypothetical value, we said, right? Often we're not actually going to do that in a lab. Often being one word, not two. Often a hypothetical value. But we're going to use it to calculate the overall enthalpy change for our reaction. So I'm just going to give us an example. I think the easiest way to learn how to do it is to just go through an example. So we're going to calculate my enthalpy change for the following reaction. And so the reaction, I have 2 sodium peroxide, so Na2O2, and that's a solid. I'm reacting that with 2 water liquid, and then we're going to produce 4 sodium hydroxide, solid plus 1 oxygen gas. And then we're going to be given our standard heats of formation, so we'll be given the values. They generally would be provided with the problem. If they're not, then you can look them up. There is an appendix in our book where you can find those values. I'll generally just give them to you with the problem though. So my standard heat of formation, My units on it are going to be kilojoules per mole. I'm just going to write it on the heading, and then I don't have to write it for all my values. So for sodium peroxide, it is a negative 425.6 kilojoules per mole. For oxygen, it's actually 0. And most of the time, I actually won't give you that value. I would leave it out because I want you to know that it's 0, right? Remember the definition of heats of formation, right? We're actually forming a substance in its most standard state from the elements that make it up in their most standard states. So for oxygen, right, my delta HF naught, did those guys upside down, right? What I'm doing is I'm forming O2 from its most stable, right, from the elements that make it up, which is oxygen, in its most stable form, which is O2. So as far as my change goes, right, my final is actually going to be equal to my initial. So my change then is going to be equal to 0 because I'm making O2 from O2, right? I'm making it from the elements that make it up, which is oxygen, in their most standard states, which is O2. So something like that, it's enthalpy change for formation, right? My standard heat of formation is just going to be 0. And again, most of the time I won't even put that in the table. I will just leave it off because I want to know that you know what it is, that it is actually 0. My value for sodium, oh, I wrote that first one wrong. Sorry guys. This is the value for sodium hydroxide. It's important that we fix it because one's a reactant and the other's the product, and I would get my answer way wrong if I used it incorrectly. Sorry about that. Negative 510.9. The notes that I made with this problem on it that I'm copying from, my handwriting is so sloppy when I don't try to be neat. I know my handwriting's generally sloppy, but it gets way worse than what you guys witness. Negative 285.8. If you are looking up these values, also be careful. This is water liquid. If I was to get the amount of energy that it needs to make water in its gas form, it's going to be a different number. So the states are important. If you look up those values for yourself, make sure you pay attention to the states because water liquid and water gas are both going to be listed and they're going to have different values. So it is important to pay attention to those states. So essentially everything that I've written down right now, except for this one, which I already told you I wouldn't give you because I'm testing you on the fact that I want you to know that it's 0. But all of this would be provided. So you would have this, or I would give you a table that has all of like the heats of formation in them, and you would just have to look up the specific ones, making sure that you get water liquid and not water gas. So our formula for calculating it then, our overall enthalpy change for our reaction is actually going to be the sum of the products minus the sum of my reactants. So my sum symbol, and then I'm going to throw an N in there because I do need to multiply by the number of moles that I have, right? Remember, my enthalpy changes here are kilojoules per mole, but if I have 2 moles, then I need to scale that up by that factor of 2. So N is representing my number of moles. And then we're going to do heats of formation for my products. And then from that, I'm going to subtract the sum of the heats of formation for my reactants. So I'm going to take my corresponding enthalpy change. I'm going to do products first. So I'm going to take this number. I have 4 sodium hydroxide, so I'm going to multiply that by 4. I am going to actually write this in there just so if you're using this example to kind of follow along for other examples, you don't forget that you actually have to add them together. So I'm going to take 1 and multiply it by 0 and actually write that down, though mathematically you don't need to. And then from that, I'm going to subtract. I have 2 sodium peroxide, so I'm going to take 2 and multiply it by its value. And then to that, I'm going to add 2 multiplied by my number for water. And let's just do the work right here. I'll do it in 2 lines. So products first, I have 4 sodium hydroxide, so 4 times a negative 425.6. And then to that, I'm going to add, because I want the sum, I have 1 mole of oxygen and then multiplied by its value. And then that all goes in brackets. And then from that, I'm going to subtract. I'm going to do my products. So I have 2 sodium peroxide, so multiplied by its number. And then sum again, so I'm going to add. I have 2 water, so multiplied by its number. And then that goes in brackets also. So the sum for my products, right? This is my products. Minus the sum for my reactants. And then I know this is going to sound kind of weird because it's just addition and subtraction, but the biggest mistakes I see are people just doing this math, right? I have a negative value and I'm adding it together and then I'm subtracting more negative values. Sometimes they're positive, they're not always negative. So just be really careful to keep track of your signs when you're typing this into your calculator. It really is like the biggest mistakes. Folks will set it up right, they'll do the chemistry fine, but then when you type it, not you personally, but when some people type it into their calculator, maybe it's you, you goof it up. So just be really careful. And I should stop talking while I do it so I don't goof it up, because I am just as likely. So I ended up with a negative 109.0, and then I didn't write all of my units, but all of them are kilojoules per mole. So kilojoules per mole multiplied by a number that doesn't have units. I guess the number of moles, you could just write kilojoules and it'd be fine, but kilojoules per mole plus kilojoules per mole minus kilojoules per mole plus kilojoules per mole, or kilojoules per mole. Sig figs, I'm adding and subtracting, so I went digits after the decimal place. This is just here as a reminder that we have to add it together. So 1 after the decimal point, 1 after the decimal point, 1 after the decimal point, so 1 after the decimal point.